first one is from Dimi called "Use Site Checking Considered Harmful?" Stage is yours.
Thank you very much. Okay, don't clap now, you don't see the presentation yet. So, hello everyone, my name is Dimi Racordon. It's impossible to pronounce if you're not French. Or French speaker, I'm actually not French. I'm a postdoc researcher at EPFL in Switzerland, and I'm working on programming language design and implementation. Today, I'd like to give some of my perspective on type checking. More specifically, I'd like to talk about the distinction that I draw between use site and declaration site checking. Don't worry, I will define these terms. These perspectives have been forged by my experience as a developer, but also as a language designer and implementer, and also in the context of some work I've done with Chung, who is my co-author, on a type system for Julia. So to set up the stage for my argument, I thought it might be relevant to give just a little about my own journey into programming. My training got me to experience many programming languages, but the first I got really into was Python. And I guess it's also the case for many people, but if I want to make myself a little special, I can say that I'm just old enough to have used Python before it was cool. We're talking 2.7, so right before the big transition to Python 3. And I was an actual zealot. I even had this XKCD on the door of my office for the free third year of my PhD, and I would defend every bit of Python in any programming, silly programming language war I would find myself in. And because I'm a very opinionated person, I would find myself in a lot of silly language wars. And I was preaching the usual arguments, right? Dynamically typed languages, or they enable rapid prototyping, exploratory programming, they are super expressive, and they're fast enough for the vast majority of software needs. So who would even care about static typing, right? It's clearly bad. And well, if you know me, now I preach a very, very different message. So what happened? When one day I had to learn Swift. Because I'd been tasked by my supervisor to update the supporting material we had for a class. And we wanted to have a statically typed language because we wanted to relate formal aspects, the course formal methods. We wanted to relate formal aspects to a static type system. And my life literally changed after that. So I remained a Python advocate for a little while, but I remember one day that there was one specific program that changed my mind. I was trying to implement the ahochoracic algorithm, so it's a thing with prefix trees, and I spent several hours on a stupid bug. And for some reason, I said, OK, I will just rewrite the whole thing in Swift. And well, there you go. I got a very simple, beautiful typer showing me what was the problem. So maybe this entire thing about rapid prototyping and exploratory programming was actually a sham, right? So a few months later, I removed my XKCD paper, and well, I fully transitioned to the static typing side. And sadly, I don't remember exactly what was the nature of the bug, but I can guess it boiled down to something like this. It's a completely different function, but it's to express the same idea. We're looking at a straightforward implementation of a mean function, and it does the obvious thing, right? You just add everything, and then you divide by the number of elements in the list. And this function is somewhat correct in the sense that if we test it with valid input, then it will produce correct results. The problem is that we really didn't specify what valid input means, right? And I would claim that under-specification is a plague that happens in nearly all code bases. I very rarely see a function that is properly documented, and I have to confess that I'm sometimes guilty of this problem too. But at the very least, if you have a static type language, you have a leg to stand on because you could say that there would be types in the signature. But anyway, what happens if we call this function with something that doesn't expect, that the function doesn't expect, let's say, for instance, a character string? Well, we got an error, of course, and that's great. It shows that Python is actually safe. The language will have our back if we make mistakes, and that's infinitely better. That's what we would get if we run into undefined behavior if you happen to have the misfortune of working with C or C++, for instance. And I also think that this example, if I have to defend Python a little bit, shows that we should really stop with these untyped languages. There are no untyped languages. Python is a typed language, so is JavaScript, so is Ruby, so is R. Right? These languages have a type system. They are safe for the definition of safety that we use in our paper, and so let's stop calling them untyped. But nonetheless, I think there's still a problem with this, otherwise I would be talking here, and I think I can capture my objections with 3 questions. The first is when the error was reported. Now, maybe some of you were already there on Sunday, and we had a talk by Benoît Combal, who told us that the distinction between the various time of software development are kind of meaningless, and there is no distinction between compile time and runtime. Well, I happen to utterly disagree in this case, because if I'm a library author, then there is clearly a time before and after I ship my code. And if the error happens in the user code, then I don't see it until the user is like maybe submitting an issue to my repo or whatever. The second question is where the error was reported. And here the issue is from the perspective of the library user. They're getting an error that's reported in code that they didn't write. And so it's not obvious what they are really supposed to do. As we've established, the signature of the function was not clear. So you could claim that it's nonsensical to try to find the arithmetic mean of a string, but maybe the next person is thinking that you should get the arithmetic mean of the ASCII value of every character. You don't know, the signature didn't tell, so the blame shouldn't be put on the user, and the user shouldn't have to deal with this error. And the last question is how the error was detected. And here the issue is that neither the library author nor its user can see the color of the error until they have a problematic input. So chances are that the problem, like this problem with the min function, can go unnoticed for years. And then when we eventually show up, it will be all the more surprising, right? This fantastic statistic library has been used for years, so surely it is bug-free. So those things are issues, and I think that if we care about a good user experience, we should have the same answers to this question. When an error should be reported? Well, as soon as possible, and that means when I'm writing the error. Where should it be reported? As close as possible at its origin. So as the author of the error, should have the blame. And how it should be detected? Just by looking at code. I shouldn't have to find examples of problematic inputs so that there is a problem. Now, focusing on these 2 first questions, let's see what happens if we write all of this in a statically typed language. And well, I said that I fell in love with Swift, so I will use Swift here. Now we have a statically typed version of this function, and if we happen to call it with a string, then we get a beautiful error. So it's also easy to place the blame now. The blame is on the call side in this particular instance, because it's clearly not satisfying the precondition, which is not written in the comments, but actually is written in the signature of the function. So partly because of that, I think it's fair to say that static typing has won over a lot of people. I'm not the only one to be in this camp anymore. And it's no longer controversial to say that the benefits of running a type checker ahead of time are worth losing some of the expressiveness. I will come back to the expressiveness because you could clearly argue, well, this function is clearly not as generic as the one before. And so I justify my claim that static type checking has won by the fact that Python and JavaScript, who were once poster children of a dynamically typed languages, are now typically used in conjunction with some form of static typing. But OK, why I'm saying all of that? There's been already countless arguments and debates about static versus dynamic typing. And I don't really have anything new to add to the conversation. All I've said here are things that you might find even in blogs if you look on the internet. And I'm not here also to convince you that you should abandon your dynamically typed language. If you are still a Python lover or JavaScript lover, all the power to you. Instead, the point I'd like to make is that some of the arguments that we now confidently use against dynamic typing, so the kind of argument that I just used now, should also be used against static typing, or at least some form of static typing, which I call use-side checking. So to understand, let's rewrite again our min function, but this time in this terrible, terrible C++ language. And let's start with a non-generic version of the code, one that only works on concrete types. And well, because C++ is this terrible, terrible unsafe language, we'll add a runtime check to make sure that we're not dividing by 0. Otherwise, we would be in undefined behavior lands, and the nasal demons might come. I also want to be thorough with my documentation, because I said earlier that we should better document our code. And so I will say what I preach, and then I will add this comment here. Okay, now what happens if we are calling this function with a string? Well, C++ is statically typed, so we get a beautiful error pointing exactly where it should, just like in Swift, all is well. But what happens if we want to recover some of the lost expressiveness, because this function is not as nearly as generic as the Python one? So the usually preferred way to write generic algorithm in C++ is to use template functions in data structure. A template function is a function that accepts one or more template parameters. And here, for instance, we have one template parameter in here that is acting as kind of a placeholder for a type in the signature. Notice that the function takes two arguments representing positions in the collections. Don't be mad at me. This is the idiomatic way to work with collections in C++. We actually use ranges instead of just the collection itself. And this character salad here is C++ lingo to say that it's referring to the element produced by the iterators here. So just forget about it. It's mentioning that T is an iterator, and we will get the elements of these iterators. And the rest of the implementation is exactly the same as we had before. Well, just we are now using the standard library. So a function template represents a family of functions, and each member of this family corresponds to a particular instantiation of the template parameters. So when the compiler sees a call to a function template, it will generate the appropriate member of the family by expanding the template. Right? It's pretty simple. So here, for example, the compiler will deduce that the argument of the template is the iterator type for vectors of doubles, and based on the type of x's, it will also expand the template for that type. Now, the advantage of this approach is in simplicity. If we brush over the details, the very complicated details of argument deduction in C++, we're actually left with a system that simply generates definitions on demand, and then we use overloading to select the correct implementation. So our program is roughly equivalent to something where we would have just defined different versions of mean, and then we would have used overload resolution to find the correct definition. So that's kind of nice, right? Because it's taking this very powerful mechanism to write generic code, and it's mapping this onto something that is relatively simple to understand. Now, some people might argue that overloading is evil, but as a language designer, I can tell you it's very, very difficult to get rid of overloading. So if you have overloading anyway, you might as well use it. But the issue with this approach is that nothing prevents the compiler from expanding a template with an input that doesn't make any sense. So a matrix or a character string. So what happens if we try to do that? Now we are pass a character string, and where is the error reported? Well, now it's reported in the definition of mean. So all my complaints about dynamic typing come back. In particular, this example demonstrates that we have lost local reasoning. Most static type systems get a lot of mileage from the fact that we can use the type signature of an operation or type to reason locally about the behavior of this abstraction. But that's not the case here, because if I want to understand the error, I need to look at the code of mean. And again, mean, it might be a function that I didn't write myself. A related issue is that the signature of this generic mean says nothing about what T is supposed to be. So we are, again, back to the problem of dynamic typing. I have very poor signatures here. We can only guess from the documentation and maybe from the name of the parameters. But even if I use a more meaningful parameter than T, the compiler won't do anything to check that this meaning is related to the code that I actually wrote. And this problem was actually discussed by Alexander Stepanov, who's the father of C++ first original standard library, back in 2002. He made this point with a slight version of this program in a presentation that it made at Adobe. And here we're looking at a possible implementation of the reduction operator, or fold left, for people who love functional programming. And this function takes two generic parameters. We have the type of the iterator representing the container to reduce, and the profile of the binary operator to apply. Now let's focus on the first one here, which is called input iterator. And has some meaning in the C++ community, but I will come back to that. Now, the body of the function is not very surprising, but I understand that you might not be comfortable with C++, so we can quickly look at what it's doing. First, we check whether the range is empty, in which case we exit early. Then we allocate an accumulator, initialize with the first value of the range, and then we combine each element in a loop. And finally, we return the basic implementation of the reduction operator. Now, in C++, it's common to name template parameters after meaningful concept. So, for instance, here I used input iterator because the community in C++ generally understands input iterator to be a pointer-like object that can be dereferenced with the star operator, and so to access the value pointed by the iterator, and the iterator can be advanced to the next position using the ++ operator. But some of you now may note that this specification, so I can dereference and I can advance, it's leaving two other operations out of the picture. So the first is that I used here an equality operator between the two iterators. This was not part of the specification that I just said. And I also used a less than operator in the loop here to know when I exit the loop. And this is simply not part of the specification of input iterator. So again, it's underspecified, even if the name is just like a comment. So not only this signature is not better than a comment, but also we have missed additional requirements that we should put in place here. And again, the compiler doesn't help us to detect that in any meaningful way. So what makes this problem extra perverse is that we're likely to satisfy these extra requirements in the unit test that we will write, because most common data structures in C++ have iterators that are actually more sophisticated than just input iterator. So for example, the iterator of a vector is a random access iterator that happens to support equality and comparison. So all is well here. I can write this unit test, and I will be very happy with my library, but it will crash in the user code because maybe the user decides to use a less sophisticated data structure, such as a linked list. And the linked list doesn't have a less than operator, and so now we get, again, a very confusing error in the body of result. And the blame should clearly be on the library author. I did not properly specify the function, but to my credit, the compiler couldn't really help me. So this is getting into the how the error was detected. Now, I'd like to say that these requirements, like the comparison, for instance, I like to call them stealthy, because these are the kind of requirements that are usually satisfied by the code that you would normally pass to the function. And so they are extra hard to find. They are extra hard to know that you need to specify them. Right? It's easy to focus on the unusual operations, but those stealthy operations that happen to usually work for most types, it's a bit more, it's a bit easier to miss. So yeah, it gets us back to how the error was detected. So if you ask me, this entire situation doesn't really uphold the properties that we usually ascribe to static type checking. In particular, here I was able to write generic code that is actually not well typed, but I had no idea until I ran my code. Here, running means compiling the code with some actual use cases. And the last issue I'd like to talk about is what I call type imposture. And to illustrate, we can go back to the original example with the min function. And setting aside the problem of specifying what kind of iterator is needed, there's another requirement here that we can look at. The elements in the range must be divisible. And so maybe you're a C++ advocate and you say, oh, but in C++20 we have concepts, so we have solved this problem that you're mentioning. So there is a way to express the requirements, and there is a way to make sure that the compiler checks that the requirement is satisfied. So maybe we don't like the syntax, but well, at least the concept exists. We can define here divisible as a concept describing types that have a division operator. And now we can use this concept in the signature of min to express that the requirements must apply. And so if we try to call min with a character string, then now we get a beautiful error. So problem solved, right? Let's go home. Well, not exactly, because first there was nothing that compelled me to use the concept in the first place. Like, it's purely an opt-in. I decided to add the concept, and if I didn't, the compiler was happy to accept my underspecified function. But it's also easy to accidentally satisfy this concept in a way that min doesn't expect. So, for example, what do you think happens if we call min with a vector of path, right? Well, it works perfectly fine because path happens to have a slash operator for concatenating paths. This is actually quite common in libraries that have paths. And we are back to square one because, well, we just had a slash operator, but it doesn't really implement the thing that we wanted. So this example reveals that C++ concepts do not address any of the issues that I mentioned. At best, they are a way to sometimes bring error messages closer to their source, or make slightly better error messages. But, well, if you ask to veteran C++ developers, they will sometimes tell you that they deactivate this concept because it actually makes worse errors than with just the templates. So this is not really a very great situation. So beyond C++, because it would be easy to say, well, OK, but this is a C++ thing, right? I don't care about C++ anyway. The thing that is interesting is that the concepts here that we have used, they relate to another form of type checking that we do in dynamic type languages, which is type validation. Right? You can have your you can have your function in Python, and then in Python you could like add this kind of silly code at the beginning of your function to catch early the errors. You can even use very nice libraries like Pydantic to reduce the boilerplate here, and then you would have described a sort of concept, just like C++. But the fundamental problem in all of these examples is that the generic codes happens to be checked at use site rather than declaration site, right? I need a concrete use of my generic code to detect any possible error. So when I declare, and that's not what we expect for static typing. When I declare a concrete function in C++, like this definition of min that is not generic, then the compiler can report the errors. And the reason it can do that is because the signature acts in two ways. It serves two purposes. Inside the definition, it is a sort of set of axioms, a source of truth that I can use to type check the function. And everything that is beyond this source of truth, that is not specified in its source of truth, is considered an error. So, but in the generic version, then I lose this source of truth because nothing happens until my definition expanded. So use-side checking doesn't give us the benefits of static type checking. It doesn't give us local reasoning, and it doesn't give us the guarantee that the code we write is actually well-typed. And this is exactly the kind of issues that we would expect from a dynamically typed language. The only difference is that the errors still occur before the code runs, but they occur at the time when we are running the type system. So why do I think that this analogy is interesting? It's because in our transition from dynamic typing to static typing, at least in my own journey, we found solutions. And I think there are two paths that we can take. The first is that if we want to insist on dynamic typing, well, we can look at how we debug code in dynamic type languages. And in that sense, we would need better tools to test and debug template expansion. For example, given an error like this, I'd like a way to inspect all the intermediate steps that led to this point. Perhaps we could even imagine step debuggers into the template expansion. And then I could use all the techniques that we have developed for debugging dynamically typed languages applied here for this kind of template expansion. But if you're in the side of static typing like me, we would reject that, right? We would want to have like true static typing. And so here the solution, if we look at what we did from going from dynamic to static, is to just create more sophisticated type systems that are able to describe the patterns and abstraction that we want to describe in the dynamic part. So there are plenty of languages that are actually able to do that. So for instance, we can write a generic min function in Swift and have it checked at definition side. So this function is well typed, and every use that is satisfying the precondition of the type system here will mean that this function does type check. But Swift is not the only language that can do that. We can do the same in Scala, or we can do the same in Haskell. The point here is that there are already well-established type systems that are expressive enough to check relatively sophisticated abstraction at definition site. In all of these systems, the key observation is that the signature takes on the two roles that I mentioned before. It describes the axioms at the definition site, and it describes constraints at use site. The constraint we get with the type validation approach of the concept, but we don't get the axiom part. So if we focus on the Swift version, for instance, we can see that this constraint here assumes that reduce exists from this because T is a collection, so it does have a reduce method. And this constraint here lets us assume that addition and division between the elements of the input collection is defined. And if we remove either of these constraints, then the function no longer type checks. And so I have all the properties that I expect from static type checking. And at call site, the constraints apply in the same way C++ concept would apply to, and the errors are reported at their origin as one would expect. So in other words, my 3 questions get the correct answer. Now, one may complain that, well, this is all fine and well, but these type systems are very complicated. Right now, you need protocols, traits, type classes, you name it. And that is true. There is no free lunch, right? If we want to have a type system that are expressive enough to express the things that we do with dynamic typing, then we need to buy into some form of complexity. But I think as a community, we have grown a lot, and now we have normalized a lot of the features that we find in those languages. iOS developers every day use protocols, so they use type classes every day, and now we have completely normalized that. So the transition that we've done from dynamic typing to static typing, here I think we also need to apply from simple static type system that use template expansion to more complex type system that use type classes or bounded polymorphism, or you name your favorite feature. And I'd like to stress that I used all my examples here in C++, but this template expansion mechanism can also be found in other new up-and-coming programming languages. And so this talk is and my essay is really a warning to language designers out there. Please don't do that. This is extremely bad. This leads to very bad user experience, because if you want to have a static type system, then please create a static type system, or at least give me the tool to debug the errors that happen during the type checking of my program. OK, so I think I can wrap up here my little rant that I gave about programming. Thank you for indulging me. But really, the key takeaway here is that use site checking should be considered harmful. This was my opening title, because the reason is that it doesn't bring the benefits that we ascribe to static typing. It is nothing but a cheap way to improve on the expressiveness of a type system. Right? It's very simple to implement, and so you might be tempted. Right? You have your simple type system, say, oh, yeah, I need a generic thing now. OK, let's just add template parameters. But yeah, then you get all the silly issues that we've discussed today. In particular, I think it comes at the expense of the user experience. And here, I think this is important because this is another key aspect that we often miss. If we just focus on saying that this is sound, then yeah, sure, but Python 2 is sound. So if the argument is to say, but this is a sound type system, just use a dynamically typed language. It's also a sound type system. So we want more than just soundness, because Python is kind of sound in the most useless way, right? It sounds just up until the point that you will crash. So well-typed program did not go wrong because you threw an exception. So here, well-typed did not go wrong because, well, you didn't compile, but you couldn't understand the error. It would be like saying, yeah, sure, the best type system is one that never compiles anything. This is perfectly sound, right? Your program is wrong, maybe. I don't know, I won't compile it, but don't worry, now it is sound. So I think we need to focus more on the user experience of using these systems so that we can use them efficiently. It's not just about soundness, it's about harnessing the power of a static type system to help debug silly bugs, such as the one that I did when I was still young. So if there is any language designer in the audience, if you know any language designer, please consider my arguments. And with that, I conclude my rant. Thank you very much.
Thank you for the talk. So I will start with a question about error messages and how to motivate the programmer to fix them. Could be through tools. So if you go back to slide 33, I think, with the message that element was not a floating point, right. But what did work out was, yay, it's at least a collection. What do you think about giving hints what worked? And I think this is a more general thing, how to treat these messages like, okay, this checks out, but you missed to adhere to element floating point.
Yeah, definitely. So the first thing that I should mention, in again a kind of defense of Swift, is that I shortened the error messages because Swift is a bit nicer. Still, it's really not to the point where it has nice error messages, but it's better than the nonsense that I put on my slides. But yeah, exactly. I think it's very good when you have an error message that tells you the most that's the type checker was able to do. And I really want to emphasize on this. We need to understand what the compiler is trying to do. To me, programming is a lot of time a dialogue with the compiler, and that's why I fell in love with static typing, is because I can communicate a little more with my compiler, and I want to be able to form a mental model of the compiler went there because of this and that, and now I can understand why I end up in a situation where things don't work. So yeah, clearly, better error messages are needed.
Hi, I had a question about your example with the C++ concepts earlier. And also, I hadn't really seen them in detail before, so this is a nice explanation. I was surprised that, in fact, they are not really good enough. I was hoping, I guess the little bit of hubbub I had heard about concepts was they were this great thing, but it, obviously it seems they still have issues. I guess I sort of have a two-part question. One is do you think there's a way they can be saved by adding something to them? And then also, not you explained why they're not good enough. What are the issues? I guess I'm what were the constraints? If you know, or you can suppose, that caused the designers to put in this system that still isn't good enough. My guess is maybe needing to maintain backwards compatibility with previous versions of C++, but I wonder maybe there are other factors that or can guess at.
No, so as far as I know, it's exactly that. So the story about concept in C++ is very interesting. So there was a group working on a design for the concepts. I think it was back in 2008-ish or something like that. And they had something that's ended up being the Rust rates and the Swift protocols. So exactly the same people went on to achieve their vision. And the entire proposal was ready to go, right? It would have been the nice thing. It would have been the Rust rates inside C++. So we could have had nice things for once. But there is a lot of infighting at the high levels of C++. And at literally the last minute, it was pulled off. And replaced by these lesser concepts, because one very important person in C++ that I will not name, but I guess you can figure out who that is, didn't like the idea of having to explicitly declare conformance to a concept. So they wanted that if you happen to satisfy the requirement, then it should work. And so we got into that. In the defense of concept, I will say that it is a very expressive system because you can have arbitrary compile time assertions. But this expressiveness is kind of the same thing as type validation in Python, right? You can run arbitrary code to validate your type in Python, but this expressiveness comes at the cost of not really having a type system. So there are trade-offs, and I think C++ made the wrong choice, but this is my subjective opinion.
Great, thank you so much.
So this is really a follow-up to the first question, which is thinking about what advice you would give to language designers designing compiler error messages in the context of call site checking, especially with traits. Because, well, we were talking about this a little bit over lunch. In Rust, this is a big problem. Increasingly, people are, like, what happens is, can you go back, for instance, to the error message with in the Swift case? Right. You look at this error message and you go, why does string element have to conform to floating point? And in this case, it's somewhat comprehensible, but in the Rust case, it's like, your foobar does not need to baz in this, or your foobar must be baz with this associated type in this case, and then this like 300-line type needs to implement this other thing. Like, it's when the error messages start to become expressed in this fully like logical setting where everything is described in abstract types, and especially learners have a big struggle relating that back to the concrete situation that they're actually in. Now, the solution that Rust has tried to approach is basically library authors can attach domain-specific error messages to certain cases. So like, if something doesn't implement this trait, then add this a little bit of help text. Like, I don't know, from thinking about this problem, do you think that's the best we can do? Or are there better approaches to constructing these diagnostics if we accept that call site checking is the thing we want to do with traits and type classes?
I didn't know that Rust can do that. I think it's very interesting, but I would be a bit reluctant. The thing is that I think it pushes a lot of burden onto the library author, who now needs to not only understand what Rust is doing, but also like hacking their way into writing good error messages. And I think this also will be very brittle, because now what happens if Rust decides to switch their trait system, which they will do. So yeah, interesting, but a bit skeptical. I really think that as language implementers, the best thing we can do is to be more transparent about what our compiler is doing. And I think, like, in general, we are trying too hard to hide things under the rug or behind the covers of what the compiler is doing. We are like obsessed with the idea of it's magic, it works, you don't need any annotations because everything is inferred. And I think this utterly fails, because if you really want to, yeah, sure, in the correct case, this is beautiful, you have a very concise code. In the case that doesn't work, then you do need to bring the annotations into the mental model of users. So I think what you can do is to say, well, let's be very transparent about what I'm doing. So the drawback is that you close some doors to later change completely what you wanted to do, because now you are a bit more open. But if you do that, then you empower the user to understand what the language is seeing in your program. And so, for instance, if we look at Haskell error messages, they could be improved. But one thing that I really like is that it says things like x should have been int in this expression, which is in here, which is in here, which is in here. And we can get a sort of trace of why the compiler ended up with this set of assumptions.
OK, thanks.
Maybe a follow-up to the follow-up.
Yeah.
What would you think about for the library creator, maintainer, to have these configuration hooks, maybe just the commentary hooks, so that he could or she could well explain for any error message that comes through here or there, enrich it with this piece of information or something, because this is all like language level, type system level, and so on. It's not like domain specific. It's not like there can be an information that's bound to the mean function, except maybe for class names or so on. What would you think about that, to give the library maintainer some flexibility? Maybe thinking from your Python experience, where things look maybe a little bit more dynamic. I don't know. You can.
Yeah,
you can
sure.
Recall, yeah.
I think it's completely fine, and I think it's a very cool idea. And following up, I think it's very great to empower users to specialize their systems, especially because like embedded DSLs are instantly popular when your language is expressive enough to write any form of embedded DSL. So I think it's very good. Again, I think you need, for that to work, you need to have some transparency, because also the library author needs to understand how this hook will be activated, right? So it needs to be part of making explicit what the static typing is doing. And this idea of doing, so the idea of having strong type system and very expressive type system is not incompatible with the idea of being able to have a step debugger into the static semantics, right? I think this is very powerful to be able to say, okay, my code doesn't compile. Maybe I can try to work with the type inference to see what the type reference is doing, and can print this set of current constraints, and then I can say, okay, let's pick this constraint, and then I can see, and I can do this exploratory programming. If I had to shorten a little, I would say, let's just make it possible to have a dialogue with the compiler.
On that note, let's thank the speaker again.
Thank you.